Welcome to Lecture 5 in Physics 10 in 30 lectures. We finally start dynamics, a study of causes of motion. In this lecture, we will cover Newton's laws of motion and introduce the fundamental concepts of force and mass, giving some examples to illustrate the Newton's three laws of motion. We will defer the discussion of specific types of force and their unique properties to the next lecture. First, we start with an overview of the part of Chapter 2 that covers Newton's laws of motion, sections 2.1 through 2.5. The overview ends with a summary of Newton's three laws of motion. Then the rest of the lectures are devoted to illustrating the examples and some counterexamples of applications of Newton's laws of motion. The first segment illustrates the forces in an accelerating vehicle to explain the sensation we feel of being pulled backward in a car accelerating forward in light of Newton's laws of motion. Then we look at a homework problem distinguishing things that are forces from things that are not forces. Mainly a force is a push or pull. An object may be experiencing or exerting forces, and an event may involve forces. But those things are not themselves forces. And we highlight why some of us might feel like Newton's second law is not true by spotlighting the role of friction in everyday examples of motion. The remaining three sections, this lecture has a lot of sections, are meant to illustrate, explain, and demonstrate the Newton's third law, the law of interaction that I think is most often misunderstood and misapplied of Newton's laws. By the way, one confession, other than the chapter overview recorded specifically for this set, the rest of the lecture videos here were actually used section for section, cut for cut, for my Physics 4A lecture 4. I am reusing all of them here. But I have a good reason. All the video clips here were actually originally recorded for my Physics 10 class years ago. So even though this particular edit has been used for my calculus-based general physics class, nothing here requires anything beyond the conceptual physics class does. And one reminder, when you see chapter and section numbers in the older videos, please remember that there have been shifts in numbers. What appears as chapter 3 in older recordings is our chapter 2. And all the section numbers are shifted back by 1. So if you see chapter 3, section 4 covering Newton's third law, that's our chapter 2, section 5. Thank you. We start with the chapter 2 overview, part 1. We are finally getting into chapter 2, dynamics, looking into causes of motion, or Newton's laws of motion, which describe how motion is caused by what we are going to call force. Now, in this lecture, we'll cover mostly Newton's laws of motion alone, without talking about specific types of force. We'll save that for the next lecture. So in this overview, let me call it part 1, we'll cover the first half force of chapter 2, sections 2.1 through 2.5. So in sections 2.1 and 2.2, we start out with the fundamental concepts, namely defining force and mass, which will come in as we talk about force. So when we define force, this is where we have to be careful not to be circular. We can say force is what causes motion. Then what is motion caused by? It's caused by a force. So at some level, there isn't a way to avoid a certain degree of circularity, but just so that we are at least pretending that we are not being completely circular. Let's say force is a push or pull. I think that's the most clear, intuitive way to describe what a force is. You imagine something that's pushing or pulling something. That's a force. And a lot of the examples you will see in the next lecture will be what we call contact force, so you can literally see what's pushing, what's pulling. But we'll also have non-contact forces, where nothing is obviously touching something else, but there might still be a pull, or later on in the semester, a push. So we'll start out with that as giving us intuition for force, push or pull. And it's a vector quantity. As you can see in the description, push or pull, the direction matters, and the direction in full two-dimensional sense matters. But we are gonna stick to mostly one-dimensional examples so that we don't have to deal with the trigonometry. And a phrase we'll keep coming back to that you will see over and over will be what we call net external force. I'll leave that for now when we talk about Newton's laws of motion. And as we introduce force and Newton's laws of motion, especially the second law that we'll talk about in a bit, an idea of mass will come in. And mass, most intuitively, you can say it's a measure of matter or just how much stuff there is. We measure it in kilograms. It's one of the fundamental basic SI unit. So you can't describe it in terms of something else that's even more fundamental than that. And in one property of mass that we will discuss as we talk about Newton's laws of motion is something called inertia. If you are thinking of inertia in everyday language, it's resistance to change. A big organization has large inertia. And we're going to make that more concrete as we talk about Newton's laws of motion. I'll leave it here for now that inertia is a property of mass. Mass is a thing. It's got other properties other than inertia. And you will see some of that, I guess, in the next lecture. Not this one, but the next lecture. Okay, so that's force and mass. Let's talk about Newton's laws of motion. There are three of them. Newton's first law, Newton's second law, and Newton's third law. They are covered in sections 2.3, 2.4, and 2.5 of the chapter, and this is what the overview is for. And Newton's first law, you might call it law of inertia. It states a body at rest remains at rest, or if in motion, remains in motion at a constant velocity unless acted on by a net external force. And this is where the idea of inertia is a little bit different from more kind of everyday understanding of inertia, where it can be kind of equated to laziness. But someone who's lazy, if they are in motion, they don't continue in motion. But inertia of a large organization, I think that kind of makes sense. If there are things that are big organization, like a corporation or college does as a kind of normal matter of business, then unless something happens to stop it, usually business as usual kind of continues. So Newton's first law says that I guess I don't want to conceptualize this too much, but you could say things happen for a reason, and unless there's a reason for things to happen, unless there's a net external force, quote unquote, nothing will happen, in the sense that whatever was happening before will just continue to happen. And we haven't quite defined the net external force yet. I think it's easier to do that with the second law of Newton's laws of motion. You could say F equals ma, or as in your textbook, the acceleration of a system is directly proportional to and in the same direction as the net external force acting on the system, and inversely proportional to its mass. So in equation form, it would be A, standing for acceleration, is equal to F net, standing for net force, divided by mass, M, standing for mass. Now, what you might have heard more popularly in culture is, F equals ma. You're just solving it for the net force, F. And we give a special unit to the quantity of force. We call it, in honor of the guy whose laws we're talking about, we call it Newton. So forces are measured in unit of Newton, and it's a derived unit. So F being equal to mass, m, times acceleration, a. M is in kilograms, a acceleration is in meter per second squared. So you could say a Newton is equal to a kilogram times meter divided by second squared. And this is probably the closest thing to a mathematical definition of force that we would have. If in some future you are not sure something is a force or not, then one way you can test it, is it a force, is by looking at is it capable of causing acceleration. If it is capable, then great, that's a force. And the care you would need to take is that it's the net external force that causes acceleration. Now, looking at the Newton's second law and the first law, you might think that these two are saying the same thing. In fact, if you are mathematically minded, you might think the second law includes the first law. Set a equal to 0, no change in motion. That's consistent with the net force being equal to 0. That's what first law said, wasn't it? I guess what I would say is that way of understanding, it doesn't lead to any serious mistakes. So if you are thinking that way, that's fine. Nothing seriously wrong with it. But in a more theoretical sense, like if you're going to be a physics major, become a theoretical physicist, the distinction to draw is the first law is a test. It's a test to figure out if you are in the correct reference frame, what we call inertial reference frame, that your textbook doesn't mention. It gets a mention when we start talking about special relativity later on in modern physics, but even in classical physics. So Newton's laws of motion, they only apply in what we call inertial reference frame. Sometimes you are in an environment, like you are sitting in a car, and things start accelerating backward for no reason. You're not pushing anything, but things start accelerating. In such a reference frame, you would use Newton's first law to see, can I apply the rest of my laws? And if you see that things are just accelerating without there being a net external force, then that test tells you that you have to stop. You can't go on to Newton's second law and the third law. So Newton's first law is a way to test if you are in a correct inertial reference frame. Once you verify that you are, then you can use Newton's second law to be more quantitative and say the acceleration is proportional to net force. It's a very subtle distinction that makes a difference when you are thinking of laws of physics much more mathematically, like an axiomatic logical system. So for the time being, if first law seems kind of redundant, yeah, it's fine. And the nature of this course being what it is, will kind of limit ourselves to situations where first law is as a matter of course math. So yeah, we won't be using first law all that much. We'll be using second law much more. Finally, we have Newton's third law to cover in this overview. And it's the most misunderstood, maybe most often misapplied law of Newton's laws of motion. Your textbook calls it symmetry in forces. I like to call it law of interaction because that's when you pay closer attention to Newton's third law when you are explicitly describing interaction in your system. So your textbook says Newton's third law of motion: whenever one body exerts a force on a second body, the first body experiences a force by the second body that is equal in magnitude and opposite in direction to the force that it itself exerts. You might have heard this in a more kind of pithy, succinct saying: for every action, there's an equal and opposite reaction. And I feel that pithy saying leads to misunderstanding. So I have a longer lecture that talks about it more. For this overview, let me point you to this section of the textbook. The section titled Common Misconception at the end of section 2.5, Reaction versus Result. Let me leave you to read it. What I will say is that the word reaction, it's a historical term. That's probably the only reason we are keeping it. reaction does not mean result, does not mean effect. In fact, in the way it's used in Newton's third law, action and reaction are the same thing. They are interchangeable. That's what your textbook means, symmetry in forces. Okay, so those are the Newton's three laws of motion. We'll talk about the specific types of force in the next lecture, and so we'll cover in the part 2 of this chapter 2 overview. One thing I thought I would do is, let me summarize Newton's three laws of motion so it's on one screen. So I'm borrowing this from an old worksheet for my other class, but it's still conceptual, so I think it's okay. So Newton's first law, unless acted on by a net force, an object at rest tends to stay at rest, and an object in motion tends to stay in motion. Or more quantitatively, if the net force, sum of all the forces, is equal to 0, that implies acceleration is equal to 0. And it goes the other way too. Acceleration being 0 implies that net force is equal to 0. So when you see acceleration being equal to 0, that must mean that when you add up all the forces, that's what net force is, they must add up to 0. And Newton's second law says net force acting on an object is equal to mass times acceleration of the object. Or another way to say it, in the same way the textbook does, would be net force acting on an object is proportional to acceleration and also proportional to mass. The F equals m times a is just a mathematical way to express this double proportionality. And as I noted before, this mathematical relationship, sum of F is equal to ma, that might look like that's implying this. And again, it doesn't result in a serious error. So if you wanna think about it that way, it's fine. For a theoretical reason, there's a slight distinction between actual implication and, first law does come first. Finally, Newton's third law, and this is why I want you to show this overview. When an object A exerts a force on object B, call this F on B by A. Object B exerts a force on object A, call it F on A by B. And these two forces are equal in magnitude and opposite in direction. Sometimes when we say equal and opposite, that's very confusing. What do you mean equal and opposite? It's equal in one thing, opposite in the other thing. Or mathematically, writing these two vector quantities, the vector force on B by A is equal to minus of the vector force on A by B. And you might have heard this in this version. For every action, there is an equal and opposite reaction. I think there's even a matrix quote. But I do feel that that way of stating this law leads to more confusion than useful understanding of the law. And also we introduced these terms, force and mass, which is necessary to state Newton's second law, F equals ma. So this is the overview and the summary of the Newton's laws of motion, which are covered in sections 2.1 through 2.5 of the textbook. Thank you. So this is the question, and I think this is one of those scenarios where people have a certain intuitions that you build up over time, and the way we describe forces in chapter 3 using Newton's laws, it's not quite the same as how you are used to describing forces in your everyday life. So here the scenario I want you to think about is just sitting in some vehicle. It could be an airplane, it could be a car, it could be BART, it could be and you have a familiar sensation of when you are as it starts to move, it feels like something is pushing you backward. That's what you remember. That's the sensation that most people are familiar with. And I want to make sure that we know how to identify the real forces in that situation.
So there are some real forces that are kind of familiar in most setting. So there's a upward push of the seat bottom. So you are sitting there, you're not being, you're not sinking down. So something is supporting you, and this is what's supporting you. And I think a lot of people may have the temptation to check this because you feel like something is pulling you back. So maybe that's the, and what I want to make sure that you don't check is that this is not it. This is not the sensation that you are being pulled backward, that everyone feels that. But the way we describe it is not as there being a backward force on you. There's an actually a forward push on you. And oh, one more. So these two pair up to, they are not action reaction force pairs, but they have equal magnitude, downward pull and upward push, so that you are not accelerating vertically. So that's the correct answer. And it's one thing to know that that's the correct answer, and another thing to feel like that is the correct answer. So what I want to hope for those of you who maybe don't feel like that's the correct answer, maybe you feel this should be the correct answer, and it's not. Um, that let me. I want to try to illustrate with a simulation how those forces appear. This is my car. Right now, it doesn't look like a car. Let me make it into a car by applying this thruster tool. It can apply some force. I'm gonna just give it a toggle key so that I can toggle its action on and off. So just so you see how it works with the simulation running, I can toggle it so that it accelerates forward. So it's like an accelerating rocket car. So, and let me build a passenger in here. So this is going to be my passenger. So, so this is my simulation of someone who's sitting in an accelerating car. And I let me just run the simulation so that you get a sense that this is a realistic simulation, even though it's very simplified. Car, accelerating, passenger, getting accelerated forward along with the car. I hope that looks very pedestrian and like what you'd expect to see. And what I want to show is, let me turn off the velocity illustration and instead now show forces. And so let me turn on gravity. And there are some force vectors that you will have to ignore, I think. Yeah. So what I would ask you to ignore are these um, actually, let me turn off gravity. That is one thing I can turn off. And the reason I can't quite turn off the normal force is that all the forces here are normal forces. So if I turn off normal force, you wouldn't see any forces. So that's why I have to keep the normal force on. So let me just identify some of the forces that I would ask you to ignore because it's not relevant to our discussion. Those forces that I'm asking you to ignore are these normal force upward on the passenger and the normal force downward on the car. So, okay, that's there, but it's not very interesting to us, so please ignore that. And we also have the normal force at the two ends of the car that's supporting the car so that it's not tilting, it's not sinking down. I would ask you to ignore these two normal forces as well. And so as the car accelerates forward, there should be some force from the thruster, and let's see what other forces appear. I don't actually know if it'll show the thruster force. Let's see. Oh yeah, it does. That's the external there. Okay. Oops. Ah, sorry, I did something wrong. Um, I think. Let's see here. I might have to change some of the scale because yeah, that scale is tiny. Okay, so this is what I'm gonna do. Uh, let me. I'm gonna make the passenger super heavy because that's going to make the required force pretty large. Okay. Wish I could just to get rid of vertical forces. That is annoying. So if I just leave it here, it's gonna accelerate very slowly. So what I need to do is I need to make my thruster force larger. But okay, I think it's kind of beginning to come together. So I'm gonna make my thruster force larger. I don't know, 50 newtons. Okay. Let me run the simulation and I will stop it somewhere. Okay. So this whole thing is accelerating, and these are the forces you see here. There's a so this thruster that's whatever is accelerating my car. That's my external force, wherever it's coming from. In an airplane, that would be the jet engine that's pushing the other things back and providing the forward reaction force. Now, what I want you to focus on are the forces on the passenger. There's a so this backward arrow here, that's not a force on the passenger. That's the force on this car. There's a force that's pushing the car backward. The only force on the passenger, the force that's here, that's the forward force. And this forward force is pushing the passenger forward. That's why if you look at the velocities instead of forces, that's why the velocity of the passenger increases over time. That's what's accelerating the passenger forward. And the only real force that's there that's causing that to happen is a forward force that's coming from the back of the car. Um, so it's I think that's the heaviest lift that we do in physics, which is where we all come with our previous life experiences, the things that our kind of raw intuition, how we are used to explaining things, um, and what we are trying to do in this class is kind of realign that intuition, realign how we describe things. That even though, yes, as the thing accelerates forward, you feel like you are being pushed backward, but that sensation of that we are being pulled backward, it's how we sense the forward push from the sick. Oh yeah, I don't think I have ever covered this. And it kind of I think look at the question type, I think I can understand why there are so many tries, because it's a matching question. There's a lot of possibilities. So sometimes you go through it, you get some right, you get some wrong, so you try it again, change some. And I can imagine someone easily doing 10 different tries trying to get everything right. And if you're doing that, that's fine. I give you 100 tries or practically unlimited tries so that you are able to do that. But what I'm hoping is at the end of having gone through this, okay, so if you've gone through that exercise, you should kind of have this as your correct answer. Actually, let me do this. I'm going to do show answer, and let me just select all those. A, B, B, A, and all B's. So things that I'm marking as A is what's a force. Things that I'm marking as B are things that are not a force. And once you figure this out, I hope you spend some time making sure that you understand why this is correct. And I hope you kind of start to see a pattern of what we are labeling as force and what we are labeling as not being a force. Here's kind of an easy thing. Every single one that's being marked as force, it has this. It has the word pull or push or push. So those are all being labeled as force. And all the things that are being labeled as not a force, like a bee or jumping off a wall, I can imagine someone initially marking this as force. And what I'm telling you is the way it's described here, it's not a force. It's because when we call something a force, we are not referring to an object, we are not referring to an event. It really refers to one very narrow thing. A force is a push or pull, something that is going to result in acceleration and all that. But where you start out with is a force is a push or pull. So when you talk about someone jumping off of a wall, well, it does involve a force. Someone's pushing a wall. So if I talked about push against the wall, that would have been a force. But jumping off of a wall, that describes an I almost said action, and I think I'm trying to avoid the word action. It describes a situation that's happening. It describes an event. And the event could involve a lot of force, but the event itself is not a force. And same thing here, acceleration of a speeding car. I mean, the acceleration, it must have involved a force for there to be an acceleration, but the acceleration itself is not a force. It's a very technical distinction. And let's see, like Earth and Sun. These are objects. Earth is an astronomical body. Sun is an astronomical body. Now, these bodies do exert a force. Sun pulls the Earth towards the Sun. That's why Earth orbits the Sun. So if this had talked about gravitational pull of the Sun on Earth, that would have been a force. Or even if it just said the gravitational pull of the Sun, it also would have been a force. But when it just says sun, sun is an object, and there's a bunch of different things about the sun you can talk about. So the sun itself is not a force. The gravitational pull exerted by the sun is a type of force. So it's something that I think for many people it takes kind of the whole semester to learn. Is that well, sometimes we physicists can be I think OCD is not the right description. It's how sometimes people can be overly literal, almost to the point of like you might be on the autism spectrum, and all of that is true. It's because that's the mathematical aspect of physics. When we are carefully defining a term like a force, we really do have to be careful, because if we define it loosely, we use it loosely, then we say a thing, we think it means a thing, and it didn't. And when you're in math class, definitions matter a lot. And in some aspects of physics, the definitions do matter a lot. Sometimes we do get sloppy and we use the words in the way that it's not the technical definition of it. But you need to be aware what the technical definition is.
The goal of this video is to reconcile a common misalignment between intuition and physical laws. Here's how you might test yourself to see if you suffer from this misalignment. Consider this question. How do you answer? Force is necessary for motion. Or, I guess, as a question, is force necessary for motion? If you answered yes, you might be suffering from this misalignment. The correct response would have been force is necessary for acceleration, but an object in motion will remain in motion without an external force. This response is consistent with Newton's second law. Newton's second law says that acceleration is equal to net force divided by mass. Or the first version you see is that the net force is equal to mass times acceleration. So what this means is for an object that is already in motion, if the applied net force is 0, then the acceleration will be 0. And since acceleration is rate of change of velocity, the velocity of the object already in motion won't change. So it'll remain in motion. If this description of Newton's second law sounded strange to you, if it didn't sound like the correct description of the natural world the goal of this lecture video is to illustrate why it might seem that way and help reconcile your intuition to our description of the physical world. The key insight comes down to this. You have to remember the friction force, which is part of the net force. Let me illustrate this with a PHYS simulation from University of Colorado. I'm going to use the force and motion simulation to describe a common everyday scenario and attempt to explain it in terms of Newton's second law, or more precisely explain Newton's second law using this scenario. So here is a common scenario. You want to move a large piece of furniture or a package, so you push on it. As you begin to push, it won't budge until you push it hard enough. Gets moving as you continue to push it hard, but if you stop pushing it at some point, it won't continue to move, but it'll come to a stop. This is our common experience, and this experience is what so far informed our intuition. And this is completely counter to what Newton's second law says, that net force is equal to mass times acceleration. At least it is counter if you only think of your applied force. As you apply a force, acceleration is obviously not increasing with the force. With zero force, you get zero acceleration. With some force, you still get zero acceleration. And even if you get it to move, when you stop pushing at some point with zero applied force, acceleration is obviously not zero. There is a negative acceleration which brings the crate to a stop. I am giving you this description not to say that this is the correct description, but to say that it's not an unreasonable way to think. Many smart people, including very smart Greek philosophers, thought this way. It is really through the pioneering work of Galileo and Newton we are able to give the new description, which is the basis of modern engineering. So let me turn on the label for the forces. This is going to make the explanation a little easier. Now, when I'm not pushing on the box, there are no horizontal forces on the box, so the net force on it is zero, and it remains at rest. Zero acceleration. When I start to push, you see that the applied force is only one part of the force. There is friction force, static friction force, that exactly balances out the applied force. As I increase the applied force, friction force increases with it to keep our net force equal to zero. So in this picture, there's actually no conflict with Newton's second law. The key is to realize that applied force is not the only force, but there may be an additional force, friction force. This friction force doesn't increase without limit. So at some point, the magnitude of applied force is greater than the friction force, and the box does begin to accelerate. When I stop pushing, the friction force, kinetic friction force, remains, opposing the sliding motion of the box against the ground. This friction force is responsible for the negative acceleration, which eventually brings the crate to a stop. And once it stops, the friction force disappears also. Newton's second law is completely valid in everyday interaction. The cautionary note is, in order to use this law, you may need to work out the magnitude of friction force. Now, it is easier to see the validity of Newton's law in a world with no friction. Imagine pushing something on a surface completely iced over, no friction. When you push the crate, even if you apply a very small amount of force, the crate begins to accelerate. With this small force, it takes very long for the crate to accelerate appreciably, but it does. Now, once the crate gets moving, you don't have to continue to push it. In fact, in the absence of applied external force, the crate doesn't come to a stop. In order to stop the crate from moving, you actually have to apply a force to bring it to a stop. You can actually do a simple experiment to verify this in your own experience. Next time you are grocery shopping and you are pushing a good cart, no broken wheels, that are loaded fairly heavily, try this and see if it's true. After making sure there's no one around you and that you have plenty of space. 1. It is difficult to get the cart started from rest. It'll take a fair amount of effort to get it to move. But 2, once the cart is moving, it is much easier to keep it moving. 3, if you need to stop the cart quickly, simply not pushing the cart is not enough. You have to pull the cart backward to bring it to a quick stop. The first, that it's difficult to get a stationary cart started, is because of Newton's second law. So when you are bringing the cart from rest, you need to accelerate it to get it to move. And with a larger mass, you need large force to get it to accelerate the same amount as a smaller mass. 2 is also because of Newton's second law. To keep a moving cart at the same velocity, you only need acceleration of 0, meaning net force of 0. You just need to push enough to counter the friction force on the wheels, because you're not trying to accelerate the cart. And 3 is demonstrating that you don't need a force to keep an object in motion. In fact, you need a force to bring it to a stop. In fact, this crate here has been moving very slowly the whole time with 0 friction. So to bring it to a complete stop, nothing does it better than friction. I encourage you to spend enough time here until this makes sense. You can find this simulation on the PHYS website, phet.colorado.edu, to play around with it. A good physical intuition is a powerful thing that lets you get correct answers without a lot of work. Not having a good physical intuition forms real barriers to learning in physics, where the emphasis is not merely learning new facts, but entirely new ways of thinking. And it's difficult to think in a new way when the old way of thinking keeps getting in the way. This is lecture video on Newton's third law. You might already have heard of Newton's third law, or a version of it anyway. But I think the version that most people have heard is more confusing than helpful. So this is the version that a lot of people have heard. For every action, there is equal and opposite reaction. And that's unfortunate, because I think for most people, this statement actually causes more confusion than illumination. This is what I mean. Take these other statements that you may have heard elsewhere. What goes around comes around. Or maybe there is no smoke without fire. Or just the phrase, cause and effect. There is one thing that doesn't belong in this group, and that's the very first statement, Newton's third law. That's what I mean. This statement causes more confusion than illumination. If, as I was listing those other proverbs or maxims, if it felt to you like I was describing the same thing as Newton's third law, I was not. This phrasing of action and reaction is really open to that misunderstanding. You hear the word reaction and you think of the verb react, which makes you think the reaction is a result of action. And I'm here to tell you that all these implications are false. None of these are meant when someone says, for every action there is equal and opposite reaction. So to make it extra clear, all these statements which may have seemed to you similar to what Newton's third law says, Well, these are principles in life. I'm not saying they are wrong, but they have nothing to do with Newton's third law. That's what I want to point out before we start talking about what Newton's third law does really mean. So, what I would really like to do is first, let's do away with this phrasing that causes more confusion than help. And let me state the mechanics of Newton's third law in a way that it won't be confused for other things. It's a more cumbersome, longer way to state it, but people have been confused about Newton's third law often and long enough that I think this extra time is worth it. So this is how I would like to state it. For every force, A exerts on B, B exerts a force on A, and these two forces are equal in magnitude and opposite in directions. It's a bit of a mouthful, so let me draw a diagram. So let's say we have two objects, A and B, and they interact with each other, maybe pushing and pulling, maybe there are magnets on them, who knows. Let's say they are pushing, and if there's a force on B by A, what Newton's third law says is there must be a force on A, and this force is by B, and they must be equal in magnitude and opposite in directions. So the very first thing to note about Newton's third law is it involves two bodies interacting. So I like to call Newton's third law of interaction. It serves as a first check on if you have understood the third law correctly. If you are not involving some interaction between two different bodies, then you are not understanding Newton's third law correctly. And it's in this context where we can properly define the terms action and reaction. If you call one of these two forces action or action force, then the other force in this pair is the reaction or reaction force. And the biggest thing I want you to see here is the symmetry in this interaction. Action force and reaction force, there's no difference between them whatsoever. If this action force was a contact force, if A pushed on B by normal force, then the reaction force is also going to be contact force, normal force on A by B. And in fact, this symmetry is so complete, we can do this. We can swap the labels around. So if you correctly identify the action and reaction force, that's what you're going to see. That if you swap the labels around, that those swapped labels should still make sense. This ensures that you haven't mistaken the relationship between action force and reaction force as being a relationship between a cause and effect or cause and result kind of relationship, because they are not. All right, let me illustrate this to you with some examples. So this is a simulation software where I can simulate things. I can create objects in here, and I can have these objects interact with each other. Let me give one of these two boxes some velocity. And when I start the simulation, that's what you see. Alright, let me do a couple things that's going to make things easier for me. I'm going to make these boxes frictionless and elastic. It makes them ideal in some sense. It makes the descriptions easier. And let me slow down the simulation speed so that I have some time to talk. Alright, double check that one of these boxes have some initial velocity, so they move. And let me run the simulation. You've seen this before. Box slides to right, strikes, and then stops. And it's this interaction that I want you to think through. As box A strikes box B speeds away because there was a force on box B pushing it to the right. And at the same time that's happening, box A is slowing down. Watch again. And that's because box A is being pushed to the left. So what Newton's third law is describing are the forces at this moment of interaction. So it says as A pushes B to right, B pushes on A to the left. And this is the result you see. And this relationship holds even when some parameters are different. Let's say, for example, let's make A heavier. I think the simulation keeps the density the same, so I'll make A twice as big as B, or close enough. And let me run the simulation and let's see what happens. So this time A didn't come to a stop, and there's a reason for that. The force pushing B is equal in magnitude to the force pushing A. But because of Newton's second law, the thing with the heavier mass will have lower acceleration. So whereas before A came to a complete stop, this time A doesn't come to a complete stop. Let me flip this around. This time I'm going to have A smaller than B. Let's see what happens then. So by smaller I mean less mass. Now this time you see A bouncing off of B going backward. And the reason for this is the same as before. With the equal magnitude of the force that the B is being pushed by, A is also being pushed. But because its mass is smaller, it undergoes greater acceleration and it results in A bouncing back. So later in the course, you are going to see this exact same scenario described in terms of something we call momentum. But I wanted to show this to you now so that you can see we can analyze this just using Newton's third law. And in fact, when we introduce momentum, you will see the intimate connection between Newton's third law and momentum. Alright, so that's the explanation of Newton's third law. Let me end this with a fun example, just so that you can see an extended series of interactions. Let me bring back the simulation, start a new screen. And this time what I want to do is I want to create a big box. Let me give this box the same properties as before, frictionless and elastic. And I want to make it a little bit heavier. I have my own reasons. So let me make it much heavier. And I need a little dot living inside the big box. Let the simulation run for a little bit. And give the dot same property as the big box. Elastic and frictionless. And let me give it a little speed to the right. And let's let the simulation run and see what happens. So as this ball bounces back and forth, I hope you see Newton's third law acting in this scenario. That as the ball bounces back and forth, called the force on the ball that makes this happen, the action force, there's a reaction force on the box around it that's causing the box to move forward a little bit. So it moves forward here, and then it gets stopped here, and then it moves forward again, and so on. So that's all. As I keep repeating, Newton's third law is the most misunderstood of Newton's laws. If you have understood this correctly, that itself is a significant achievement. That will help those of you who are going on to Physics 4A, and I guess those of you who are not going on to Physics 4A, I'm not sure what you will use this for. But until next time, bye.
So let's see. In what order do I want to do this? I guess I could answer the question here first, and then I will go into more depth beyond what you need to know to answer this question. So let me first start with the right answer. So the distinction of external and internal forces, it kind of depends on what you define your system as. So I'm going to say yes. Internal forces are forces acting into the system from outside. That doesn't kind of sound like it. That sounds external to me. acceleration of a body is mostly directly associated with the net external force without regard to internal forces. Actually, yes. And this is what I want you to demonstrate with the help of a simulation. External forces are exerted from the system onto its surroundings. Yeah, this one is, I think, meant to, I put this here to confuse you. I guess the thing to remember is that when we describe forces, we describe forces onto a body. So, eh, this, I'm actually a bit ambivalent on this one. It could be yes. My inclination is to say no, because we wouldn't really, if I were drawing a force diagram of the surrounding, then I would describe that force. I would illustrate that force as a force on the surrounding. But if I'm drawing a force diagram of the system, I wouldn't include those forces. Except that from Newton's third law, there should be a reaction force on the system. So let me not check it for now and just see how it's, yeah. So this is the tricky choice. Could go either way. So what I want to illustrate here is first this point here, that acceleration of a body is most directly associated with the net external force. So I spent some time setting up this simulation and testing it, and I think there are some aspects here that I need to show and illustrate. Let me do it this way. I'm just gonna run the simulation once, and then I will bring it back to this point and show you the features here. So I'll just run the simulation for like 10 seconds or so. So this is what it is. I think it's kind of slightly chaotic because I don't think it's deterministic. Each time you run it, it runs slightly differently. So that's the simulation. There are some features here. One is, I think that's important to explain, is that the friction between this box and the ground, it's 0. So let me show you the material property here. Friction, that's 0. And here, material property, friction, it's 0. I hope that's maybe slightly surprising, because when you saw me run the simulation, it wasn't going anywhere. And it's one thing if it's not going anywhere because friction is holding it in place, but like if there's no friction, then how is it staying in place? So that's one. And two is, I guess this particular feature didn't have to be there. I just want you to make it fun. That's why it was there. All the collisions here are elastic. That's what this parameter is. But they don't actually have to be. The fact that the collision here is elastic, it just makes it so that the collisions go on forever. But if I want you to actually make the simulation more realistic, like something that I could actually build as a physical demonstration, then it would be actually more realistic to have a scenario where as these balls bounce around, they over time slow down. So this would be what they would look like. Oh wow, they slow down a lot quickly. Okay, that was a little too much. So that was kind of why I had that set up. Let me make it somewhere in between, zero point 0.9. So they will eventually slow down, but bounce around for a bit. Yeah. And after that, I will show you one final setup that was kind of important in setting it up that way, so that you will see what you saw a few times now. Okay, so all these balls are kind of bouncy, but not so unrealistic that they bounce forever. So this is, so they'll bounce around for a while. They, over time, each collision slows them down, and they eventually come to a stop. And this is an illustration of how internal forces have no effect on the acceleration of the entire system as a whole. And in order to have that demonstration, it was important that I set up this way. Let me use this visualization tool to show if you've lost this. So these balls, they all have the same mass. I made sure they all have 1 kilogram mass. And I set it up so that on net, they have 0 velocity. So for the ball that's going to the right at like 5 meters per second, there's another ball that's going to left at 5 meters per second, and the same deal with the ones that are moving at about 10 meters per second. So so let me mess up some of these conditions and you will see what I mean. So if I have 0, so this is at rest. So I'm only keeping the balls that are moving to the right with some velocity. And when I run the simulation with that, then, so now if you look at this entire system as a whole, they're kind of moving a little bit to the right. So let me run the simulation and let's see what happens. Now, the reason I didn't want to start out with that is it's a bit chaotic because at least I guess it depends on what you choose to look at. So I'm gonna slow down the simulation so that I have some time to talk. Um, it depends on what you choose to look at. If you choose to look at a single ball, then it is kind of bouncing around. So okay, it's kind of crazy. And if you choose to look at the box, then box is also, kind of moving, stopping, moving, stopping. So it doesn't quite illustrate as well. What I want you to illustrate from the homework question, that acceleration of a body is associated with the net external force. So when you look at this interaction here, um, the only forces that you can see here are internal forces. And let me show you what I mean. So this is the view forces. And, I'm going to disable gravity because although gravity is there, they only act vertically. So I'm just going to ignore any bouncing up and down vertically so that I'm not so confused. So get rid of gravity. And let me get rid of the normal forces. Well, actually, normal force. I think I need to keep the normal force. So, so with those forces illustrated, so right now there's a normal force from the ground that's pushing up the thing. And okay, I need to run and stop the simulation carefully here. Okay, you saw a big arrow just briefly flash as this ball was striking the wall. And let me see if I can. Yeah, it is a little bit hard. So each time these balls either collide with each other or collide with the box, those are exerting a force, and they are the internal forces. And let me just, I can't quite wonder if, I wish there was a way. Okay. Oh, I caught at the right moment. So right now, the simulation is showing normal force or the contact force between these two balls. That's what these two big arrows that are labeled with the N for normal force are. Um, so, and these are internal forces. These are force between two parts of something that we have chosen to call a system. And you can see some features in these internal forces. Um, One is that they always occur in pairs. So this arrow that's pointing to the right here, that is force on this highlighted ball from this ball. It's pushing that ball to the right. And this arrow to the left is force on this ball from this ball here. And you can see that they are in pairs. And let me run the simulation for a bit and catch another one like that. Uh, okay, there's one force between this ball and here. I want to catch one with the box just because it'll be more interesting. Okay, there it is. So this ball is now colliding with the wall here. Let me just move the screen a little bit to the right. And this ball is pushing the box to the right. That's what this end here on this box is. And the box is pushing this ball to the left. That's what this end is. And these are examples of internal forces force between two objects that are part of one system. And they don't necessarily have to be separated system. They can be just all one thing. And what's important about these internal forces is that they demonstrate Newton's third law. These are the action and reaction forces. And these two labels are interchangeable completely. I could actually choose to call this the action force. It's the action of the box pushing on the ball to the left. And I could then this would be the reaction force. And if you just swap the label, then it still makes sense. You could call this the action force of the ball pushing the box to the right, and the box reacts with the reaction force to the left on the ball. So, and there there's a symmetry to this interaction, and that symmetry is why when you have these internal forces on the net movement of the system as a whole, it doesn't affect the net movement of the system, because these two pairs will just end up canceling out when you try to calculate the net force. The only thing that results in the net force is the forces from the outside, like the ground. This and here is an external force from the ground, which we have chosen not to include in our system. So this is the illustration of internal forces and their properties, and how because they always occur in pairs. That's what Newton's third law says, that internal forces one affect the net acceleration of the entire system. I think that's mainly what I wanted to talk about. Let's see here. Oh, and yeah, distinction of what is external and what is internal force. It depends on your definition of what a system is, and this is what I mean. So I've been trying to call this entire thing a system, and the thing is, no one really. I don't have to. I can choose to call this my system, and if I choose to call this single ball my system, then then let me see if I can catch it in the collision with the wall. Oh wait, few forces. Okay, it's now colliding with the wall. So if I choose to call this, let me not show gravity again because it's cluttering up my diagram. Um, if I choose to call this a single ball my system, then before I was describing this force on the ball from the wall as one of the internal forces. That's why there was a reaction force on the wall, and I have action, reaction force, Newton's third law. Those are the pairs of internal forces. But if I choose to call this ball my entire system, then this force from the wall, that is an external force. And that external force is accelerating this ball. I think I can, oh wait, it doesn't let me illustrate the velocity, acceleration, but I can do this. Right now, this ball has rightward velocity, and just a little moment later, it has leftward velocity from the acceleration due to the external force that it was just experiencing from the box. And whether I call that external or internal force, it depends on what I define as my system. When this was my system, those were a pair of internal forces. When I choose to call this my system, then it becomes just one external force. Now, understanding this distinction and the how it connects to Newton's third law, it's important because I think I say this enough times in multiple different places that Newton's third law is the most misunderstood of most often misunderstood of Newton's laws, and that's why I ask you these two relatively these two questions that I've seen people struggle with. I think it's in questions and exercise for this. And I was getting, I got requests to do this one particular question before we started the session. So that's what I'm doing now. And those two, oh, I don't remember the question numbers for those. So I'll just briefly show you the two questions where I deliberately put it in here so that people have chance to practice their understanding of Newton's third law. And I'll do one of them that I promised I would do. So this is one one question dealing with the Newton's third law. And really what's important here is recognizing which are external forces. Therefore, you don't expect to find their reaction force within your system. And which are the internal forces where you should find their reaction force within the system. And I think I had, yeah, and this was the other one. And I guess those two are actually kind of similar questions, but just because this looks a little bit more complicated, let me do this one. Oh, this diagram is super. Okay, so let me do it this way. I think if I open this image in a new tab, yeah, then I can do it this way. I'll do a split screen, show this on the right, so that I don't have to keep scrolling back and forth, which is super disorientating, and I don't want to do that. And I can actually just scroll down here. Okay. Yeah, so let me do this question. I don't think I've ever done this question before in recorded session. So this is the question. It says, consider the picture of a donkey pulling on a cart. So donkey, cart, the arrows drawn indicate different forces acting on the donkey and the cart. And the numbers in the figure are matched up with the numbers in the text below. So this is the figure that you will have available on the site. So it says each force acting on listed below match each force to its reaction force pair. If there's no reaction force pair in the list, label it as an external force. So meaning that the reaction force is on an object outside the system of a donkey and cart. And I forget what I say in the hint. Yeah. So I think with each, I think I actually say it in the hint. I say in the hint, yeah. Most of the forces below should be an external force. So I'm gonna take a lead from that, and first to focus on determining if it's an external force or not. Because if it's an external force, then I shouldn't be looking for a reaction force. I should be just labeling it as I, external force, reaction force outside the system. So let's get started here. Number 4 here, backward pull on the donkey. So when I'm trying to determine is it an external or internal force, the first thing I should think about is what is exerting that force. So what is pulling the donkey back? And I'm thinking, I guess the only thing that's attached to the donkey and could be pulling the donkey back is the cart, which is internal. So you know what? I'm gonna actually come back to that. I think I should be able to find the reaction force to that. The downward weight on donkey. So that's number 3 here. So again, I'm thinking of what is exerting that force. Weight is a gravitational force, and if it's gravity, it should be Earth that's exerting that force. Earth is not part of my system, so it's an external force. Let me just label that as an external force. Forward pull on cart. So that's number 5 here. Forward pull. Um, I think the question even said the donkey is pulling the cart. This is one of the internal forces. So there's going to be a reaction force pair somewhere. Let me skip that for now. Okay, upward normal force on cart. Number 6, that's this force here. So I'm trying to think about what object could be pushing the cart upward. And I'm looking at the things that are touching the cart or things that could be exerting gravity on the cart. And I think I just see the ground. The ground is supporting the cart, and that's what's just providing this upward force. That should be an external force because, well, ground, that's outside my system. So this is an external force. Downward weight on cart. That's an external force for the same reason. The downward weight on donkey was that was an external force. Earth is exerting the gravitational pull, and Earth is not part of my system. Backward friction force on cart. Number 8. I guess it's this one. So it says same friction. I think it's talking about the friction with the ground, meaning that's another force that's being exerted by the ground. The ground is exerting really 2 forces: the normal force perpendicular to the surface, and a friction force parallel to the surface. So another external force. Let's keep going. Forward friction force on donkey. Oh, yeah. This is how we walk around really. When we are walking, imagine this is my foot, and the way I move is I'm actually pushing the ground back, and the ground pushes forward on me. So this forward friction force, that's a force of interaction between the foot of the donkey and the ground. So ground is what's exerting that force, and okay, so that's an external force. Upward normal force on donkey, that's external force for the same reason. This was an external force. So quite a few external forces. In fact, I think I'm kind of I process of eliminated down to these two. So the reaction force paired to this must be number 5 for the pull on cart, E, and the reaction force on this must be backward pull on monkey, number 4, D. And really, that is how these two are interacting. The donkey is pulling on the cart forward, and the cart is pulling on the donkey backward. And those two forces are equally magnitude and opposite in direction, just like Newton's third law says. And and which one you label action, which one you label reaction, you can flip them around completely. You could say, oh, donkey's pull is the action force. And as a reaction force to that, cart is pulling backward on the donkey. I think that's kind of probably the natural way most of us will say. But it is perfectly correct to say this is actually the reaction force. It's because, as the donkey tries to move forward, the cart is holding the donkey back. So this holding back is the action force, and the reaction force to that is the donkey ends up pulling the cart forward. And the reason you can flip this around is that action reaction relationship is not a cause and effect. It's two sides of a simultaneous coin. So yeah. So I guess there's one more question that you can try to practice on, which is the next question, and I'll leave that for you. So I think you'll, if at the end of this week you feel like you understood Newton's third law, that itself will be an achievement. There are students in engineering physics who are still confused about what Newton's third law means. So, so that is one thing that I hope people uh, uh, will learn as they go through this class.